Hi, we're team 13343 from Pineview School in Sarasota, Florida. I'm Christiana.
I'm Chris.
I'm Pragya.
I'm Michael.
And I'm Nick.
So without further ado, here's our solution to the 2020 MathWorks Math Modeling Challenge problem. In this paper, we evaluate the possibility of the transition from diesel-powered semi-trucks to electric semi-trucks. In part one, we were initially tasked with predicting the proportion of semi-trucks that will be electric over the next 20 years, and decided to implement 3 Markov chains to do so. We separated the trucks into short haul, regional haul, and long haul, and 3 transition matrices were then used to calculate the expected percentage of semi-trucks on the road that will be electric in the next 5 years, which was 27.39%, 10 years, which was 69.49%, and 20 years, which was 97.77%.
Our second model determined the amount of infrastructure, which is primarily charging equipment, that is necessary to transition a given shipping fleet to 100% electric semi-trucks. Using 2 Monte Carlo simulations, we estimated that the ideal number of DC fast charging units at each truck stop using Department of Transportation average traffic statistics. We also found that regardless of trip length, placing a charging station every 90 miles will allow for the least idle charging time and thus the fastest total time.
Finally, we decided which corridor should be targeted for development first. We created an importance score based on 3 factors: economic growth, environmental considerations, and cost to implement the necessary infrastructure. Economic growth was calculated from the money saved by decreased idle DC fast charging time and total average traffic. The environmental consideration metric was based on electric vehicle policies in the state or states. Cost was determined using our solution to part 2. The results indicated that the Minneapolis to Chicago corridor should be targeted first.
So for our global assumption that was applied to every part of our paper, we assumed that the initial operable semi-truck population in the United States was 1.7 million. So for part 1, we defined the problem as follows. We developed a model to predict the percentage of semi-trucks that will be electric 5, 10, and 20 years from 2020. We decided to implement a Markov chain to do so because 2 states were given, either electric or diesel, and the question was about determining the proportion of electric semi-trucks in a given state during a given period, 5, 10, or 20 years. So for our first assumption, we assume that no electric semi-trucks are currently on the road, so the initial state matrix in the Markov chain is 1, 0. We could easily adjust the model by changing the initial state matrix, and in addition, the average life expectancy of electric semis was assumed to be the same as that of diesel semis, around 12 years, due to lack of data on electric semis.
So one of the questions that were posed by the judges was why we chose the value of 210,466 semi-trucks for our estimate. And so according to the given truck production data, the total number of Class 8 trucks produced has both increased and decreased over the last 20 years. And so we assumed a constant market to account for the irregularities in the production data. And since the Great Recession occurred during this time period, which may have accounted for several of the lower production values, we took note of the overall increasing production trend present in the last decade, and we used the 2019 production value of 210,466 semi-trucks instead of the more conservative value of about 160,000, which is the average annual production over the last 10 years.
So when it comes to developing the model, the Markov chain model that we created accounts for statistical uncertainties in introducing a new product to an existing market. So we set a probability of 0.01 of an electric semi user switching back to a diesel semi after seeing some relative disadvantages. The p-value represents the probability of a type of diesel semi-truck, short haul, regional haul, or long haul, being replaced by an electric semi-truck.
And so in order to obtain these p-values, we found the difference in total cost, which is made up of the operating and purchase cost of a diesel semi and an electric semi. And we determined that the calculated values caused a significant difference in transition probabilities of electric semi-trucks.
Another one of the questions posed by the judges was asking for more details on computing probabilities for transition matrices. So for each type of semi-truck, we created a transition matrix that represents a separate Markov chain. Using MATLAB, we calculated the probability of being in a given state, electric or diesel, for each type of semi-truck in a given year. In MATLAB, we calculated the state vector for each year and multiplied it by the transition matrix for each type of semi-truck. So when it comes to executing the model, we then calculated the proportion of electric semi-trucks on the market over the next 10 years. According to the third assumption, after 12 years of electric semi-truck production, inoperable electric semis will leave the market and be replaced by operable electric or diesel semi-trucks. Using our predicted values for inoperable electric semi-trucks over the next 20 years, The Markov chain model predicted the proportion of electric semi-trucks compared to the total population of semis in 20 years. And as you can see here in the PowerPoints, this is an execution of the MATLAB diagram of the Markov chain.
So our model assumes that a semi-truck is used immediately after it is produced.
So the total cost differences that were calculated earlier corresponded to the greatest proportion of electric semi-trucks for each type of semi, with all types having a significant proportion in the bigger picture. The irregular short-haul and regional haul data correlated with past irregular production data. The long-haul data for diesel semi-trucks was consistent with the predicted pattern of the production of inoperable semis, yielding a relatively linear growth. So when it comes to strengths and weaknesses,
So one of the strengths of our model is that the Markov chain model incorporates all the factors that are given to us and the type of semi-truck that is being replaced in a given year, which is one we came up with. The p-values can be more rigorously determined by analyzing empirical sales data for electric semis upon their release to the market, which is one of the weaknesses.
currently the model does not account for hybrid semi-trucks, but a third state can easily be added to this Markov chain model to incorporate short-haul, long-haul, and regional haul hybrid trucks as shown in this PowerPoint. So if some inoperable long-haul trucks enter the regional truck pool and some regional trucks enter the short-haul truck pool, the model would have to be adapted to link these Markov chains together as shown here. This model is functional with the assumption that all electric semi-trucks can serve as a long regional or short-haul truck. If this assumption was not present, there would have to be an additional 2 states in a Markov chain model to account for different types of electric semi-trucks. The p-values were determined by the ratio of the cost differences, and this would likely change due to the change in operating costs.
All right, so part 2 of this problem is all about infrastructure, specifically the most effective distribution of electric vehicle supply equipment, or EVSE, given that all shipping fleets use only electric vehicles. In this case, we define effective in terms of money and time saved. This is going to be an important question to answer because our solution to part 1 shows that it's not going to be too long before we're almost in that situation.
Real quick to answer some important questions regarding our methodology. A lithium iron phosphate battery's state of charge will exponentially approach 100%. When charging, these types of batteries act like capacitors. That is, the greater the electric battery's level of charge relative to its capacity, the more the charges repel each other and the slower they charge. That's what creates the exponential approach. They charge fast at the beginning and slow at the end. The state of charge of a charging battery can thus be modeled by the expression 1 minus e to the minus kt. And conversely, when discharging, the batteries apply constant voltage. So, energy output is constant regardless of the battery's state of charge. This means that a truck's range at 50% is half of its range at 100%. In other words, range is directly proportional to state of charge.
Okay, so moving on to the model. In order to create the most cost-effective distribution of charging stations, we need a pit stop schedule to minimize I, which is the time trucks spend attempting to charge, because, well, time is money. To approach the problem, we assume that all stations should be roughly equally spaced. So a driver charges up to a state of charge C sub F, and upon reaching a state of charge C sub 0, they stop. In this case, we assume the stopping state of charge to be 20%, which is a common strategy used by drivers today to reduce both range anxiety and the risk of running empty.
We want to minimize I, so we created a formula for idle time given CF, R, the range of the truck, D, the trip distance, and T80, the time trucks spend charging to 80%, which is a statistic available for charging scenarios. The formula boils down to number of stops multiplied by the idle time per stop. The number of stops equals the total distance D divided by the travel range with the assumed driver charging behavior. That is, the state of charge a driver charges up to minus the state of charge at which they take a pit stop multiplied by the range. And finally, we take the ceiling of this expression to avoid a non-integer number of stops. Idle time per stop was determined by solving an exponential approach equation for T and adding T to I min, the time it takes to get off the highway, pay for fuel, etc., about 10 minutes.
All right, so plugging the projected statistics of a middle-of-the-road electric semi-truck, the Freightliner eCascadia, into our model, we get this plot of idle time versus optimized max charge percentage, and it actually turns out to be 60% regardless of range or trip distance.
Now we can actually answer the question of what's the best distribution of EVSE. In order to find the ideal number of stops per shipping route, we ran a Monte Carlo simulation, randomly generating R and CF in accordance with our previous results. In order to find the ideal number of DC fast charge units at each truck stop, we ran another Monte Carlo simulation. We approached this by finding the average number of trucks present at any one time during the day. So given that one truck will spend I minutes charging at a station during a day, the chance of that truck being at the station at any time is I divided by 1440 minutes in a day. And the average number of trucks present will be the sum of this chance for every truck that visits throughout the day. Fortunately, there is a widely available statistic for this, the annual average daily truck traffic. We used a Monte Carlo simulation to simulate the idle charging time for all the trucks visiting a station in a day, randomly generating C0, CF, and T80 to approximate the assortment of batteries and charge strategies used. Finally, we used data for each corridor to find the average number of trucks present at a station on that corridor and plugged the random samples into the previously described formula. Thus, we know how much EVSE will be needed.
Okay, so before we show the results, some notes about the model. These models, like all Monte Carlo simulations, create estimates based on the best data we had access to. We believe that our underlying mathematical rationale is valid, but our results could be improved by better information about, for example, the experimental ranges of the electric semi-trucks, which will be available when they actually exist.
Here are our findings. More detailed graphs of the output can be found in our paper. It's also worth noting that for all of the shipping routes, the optimized distribution of charging stations is about one stop every 90 miles.
Now, obviously, this strategy is unrealistic for current diesel engines. However, what we've demonstrated is that even with the more frequent stopping times, the amount of infrastructure necessary to sustain a nation of electric semi-trucks is much less than the current amount of infrastructure for gas and diesel. It will be a hefty initial investment, but one of the biggest reasons electric semi-trucks are becoming more viable is the much lower maintenance cost. And that's what we think should be taken away from these models.
For part 3, we were asked to develop a mathematical model to rank the 5 corridors mentioned in part 2, determine which should begin development first. We assume that the cost per mile of semi-truck shipping is $2.75, based on the current average value. The mean cost to install a DCFC station is $22,626, based on data published by the US Department of Energy, and 50% of trucks that use the corridors are long-haul semis, which is provided on the information sheet.
To develop the model, we considered economic growth, environmental considerations, and the cost to implement the necessary infrastructure. The metrics were normalized and equally weighted to create a final importance score X, which is the sum of the normalized values of E, the environmental consideration score, G, the increase in GDP from trucking time, and S, the total cost of building the trucking corridor.
So we decided to add S, the total cost of building the trucking corridor, to the importance score because a greater cost results in a greater investment, which will yield more profit and therefore a greater importance for development.
Okay, so first, economic growth is estimated as the total value added by decreased idle times and fuel costs rising out of the transition from electric to diesel. For each shipping corridor, the dollar value V of an en route semi-truck's time was calculated as the value of a shipment, the average shipping rate multiplied by the trip distance, divided by total time. The trip time plus the idle charging time is found in part 2, using the projected statistics of the Freightliner eCascadia. Now that we know the value of a truck, a measure of the economic growth created by all the trucks on the corridor can be found by multiplying the value of 1 by the average total number of long-haul trucks, or T average.
Environmental considerations were based on the number of state policies and actions about electric vehicles, such as zero-emission vehicle policies and electrification plans. If states had set more policies encouraging electric vehicle use, they would be more likely to develop their trucking corridor. Environmental considerations were separated into 4 levels based on the average number of policies and actions the states have.
Finally, the cost is based on the cost to install one DCFC station multiplied by the number of chargers required as found in part 2. After we input the values for the trucking corridors mentioned in part 2, the results indicated that the Minneapolis to Chicago corridor should be targeted first, followed by Los Angeles to San Francisco, San Antonio to New Orleans, Jacksonville to DC, and finally Boston to Harrisburg. Thank you so much for listening. It's so important to consider the impact of diesel semi-trucks on our planet. Transportation causes 27% of greenhouse gas emissions and 75% of carbon monoxide emissions, and diesel semi-trucks are a large part of the problem, particularly with the rise of e-commerce. The transition to electric semi-trucks can help reduce our impact on the planet. We really enjoyed this opportunity to address a real-world problem, and we learned a lot.